Thank you for the invitation. Today I will tell you something about the journey of an, I would say, computer scientist into hardware design. And is this one? Ah, okay. And so I will tell you something about history. So first, the disclaimer with respect to the last talk. We are computer scientists, so we are focusing on 0 and 1 and nothing in between. I'm convinced that nothing exists between 0 and 1, so be careful. So a decade ago, I was asked to build an ignition key for a car. So formerly I worked for car industry, and it should be an ignition key based on a zero-knowledge protocol, which is cheap and fast, so faster than 70 milliseconds. And really, really cheap, 5 euros or something like that. And we tried it, and I did a lot of math for realizing this project, but we failed. And okay, and then I said, okay, I have to build it in hardware. So IDEA built dedicated hardware for this. And this was a starting point of the things we are doing at the moment. So what was given? We had no knowledge about digital design. We had no funding and no support. I had no students to help. I had no suitable curriculum because we are computer scientists. And my colleagues were not very helpful because one of my colleagues said, Steffen, you are a mathematician, so even this sentence is wrong because I'm theoretically computer scientist, so I like complexity theory. And if you ask my wife, she would tell you, Steffen is really, really stubborn, and I didn't accept this sentence, so I asked myself the question, how can we bootstrap the process to build hardware? And so I remember the very famous quote by a guy I really like. He said, if you want to build a ship, don't ram the men up to gather wood, divide the work and give orders. Instead, teach them to yearn for vast and endless sea. And this was a trick I did. So I tried to find ways to convince my students that they are allowed to build hardware for me. And so I defined some, for computer scientists, interesting, which one is there? Okay. Interesting topics, for example, for starters, some communication devices. CPUs are always interesting for computer scientists. Cryptography, because I come from cryptography, elliptic curves and AES and SHA-3, and we built some cellular automata and fractals and retrocomputing, and we reverse engineered the Game Boy display interface and transformed it to HDMI. So they were able to play Game Boy games on a very big display. It was a funny project for them. And this is a way to attract students to hardware design. Because what I realized is that we have not enough students doing hardware stuff. Okay. What is going on?
Ach nee, warte mal, es ist im Windows rüber gerutscht.
Ah. So I'm not familiar with Windows.
Probier.
Okay.
Ja, ja.
Ah. Okay.
So, okay, sollte wieder gehen.
Okay, thank you. So I learned some lessons. For our bootstrap process, we need good literature, so it was a big problem for me as a beginner to find good literature. You find literature about simulation and low-level design, but I'm a computer scientist. I'm interested in building stuff, so it's very hard to find good books. Then we need modern and productive synthesis tools. And as a talk before already said, we like to automate things. We don't like GUIs and IDEs and stuff like that. We like make files and scripting and things like that. And what I also learned was we have to attract young engineers, not the old ones. Because the young ones will do the work. And what I learned is my students hate VHDL, they hate Verilog, they hate Xilinx and Altera and Cadence. So, so maybe they hate everything, I don't know. But we have to use new stuff. Maybe the new stuff is not better, but the youngsters like it more. And we need very cheap takeaway hardware so everybody can work at home. So we started with cheap FPGAs. And this is fine because I'm always targeting on mass market applications, so cheap FPGAs are good. And the students don't have to sign NDAs or export regulations and things like that, because this is a real killer if you make digital design in your curriculum mandatory. The lawyers at the university will cry and argue at you because if your students have to sign something for teaching, it's a problem, I would say. And the industry always asks for junior developers, and I said, I cannot and I don't want to teach secret technologies. It's not my task to make your business growing. And if you remember the same situation we had in software 25 to 30 years ago, so we had all flavors of Unix, we had closed source software, we had insufficient and expensive tooling, we had a small developer community, and with the advent of Linux, so this is maybe a topic for the computer IT security guys, so it was easy to implant Trojans in software. And with the advent of Linux and BSD Unix, we got a complete new industry, we got new ideas, new developers, new business models, because open source brings together the experience of really different people and shares costs. So this is the idea to develop open hardware. So what we already have is cheap FPGA technologies and open EDA software. We are starting to make ASIC design possible for the masses. So we have not to sign NDAs, we had no license issues, and what is especially important for me, we have no lawyers. I hate them. We can use modern environments, and we can play the game according to the rules of our students. So the youngsters gives the rules, not the old guys. So the benefit for the industry would be modern hardware design is often evolved from old principles. So for teaching, it's old stuff is good enough. So we don't need 5 nanometers at the university, I would claim. Germany is strong in automation, mechanical engineering, and chemical industry. So what we need is solid and simple microcontrollers. And so I think open source at the state at the moment can help more than you might think. So because some people I talk to always say, well, but you have to make 7 nanometer chips. And I said, no. We don't have to, because we are strong in automation and mechanical engineering, and then we need rock-solid old technology. And the benefits for research would be full disclosure. So because this is the reason I liked your talk very much, because you showed layouts and stuff like that. And I had not to write write an NDA in before. And what is important, at least for the guys doing cryptography, you can compare your research results much easier when everything is open and can be open. So I would claim open source principles have major benefits, and we don't need at the moment cutting edge technology. It helps us a lot in the current state, I would say. And to show you that this idea works, I can present some nice stuff. So this is a RISC-V controller done by a student of mine. He got no reward for it. He got no credit points for it. It was simply a fun project. He did it for fun because it's open. So you can download the thing on GitHub. And this is a very small VPN router based on Linux. So unfortunately, it's only done with an FPGA, but as a starting point, so you have a VPN router based on WireGuard on Linux. The PCB is done with KiCad. The enclosure is done with KiCad. So everything is except this hated chip there. It's a Xilinx FPGA. It's done in open source simply to prove that it's possible to make small stuff, small appliances already with existing open source technologies. Okay, and now I think Thorsten will show us some other examples what we can do when we teach using open source principles.
This one's forward, I hope. No, this is backwards. Hello, my name is Thorsten, and I'm with Steffen at Hochschule Rhein-Main. And I present you some examples from what Steffen just told from the view of someone doing it inside that university. And the first is my last 10 years with FPGAs. And I started downloading gigabytes, like big tool chains. And it took me overnight to install them and to get them downloaded. And fast forward, I sat on the Chaos Communication Congress on a desk next to some people showing me the open source way to do it. And all of a sudden, things changed for me. Everything went very much easier. I didn't have to download overnight. There was just a package manager job to install things. And in a later project, which is called Quantum RISC, which finishes these days right now, funded in Germany by BMBF, we did our own way of trying to get tooling done, just like Harold said, and we tried the way of getting a virtual machine ready with all the FPGA tools. And I think another step now, we're at downloading pre-built images via Yosis HQ, and I'm pretty fine with that right now. And for the computer science students, it's very handy and very practical just to download and install that stuff and get it working. I can give students these FPGAs for only a few bucks. Every one of them is not that expensive. And I can give it away and give them a very short introduction how to get a Blinky example on one of these FPGAs. And they should be done in really like a few days to get their first examples done. Moving on to the world of ASICs in the last 10 years on my desk is 2013. It was far out of reach for me, and there was no way to get to an expensive tape out by that time. That changed like 2021 on my desk. All of the tools I'm using right now are most of the tools are quite older. My introduction to all of that was sitting here in the middle with that ASIC hat on it. Matthew, thank you for that, with a Zero to ASIC course. And that introduced me to famous things like open PDKs, like the open MPW shuttle runs, like the Sky 130 PDK. And later on, next year, I was happily with doing some own tape outs. Please remember, I'm a computer scientist, so I've never heard before of standard cells or things like that, and I was able to do some tape outs. And right now, I have the opportunity to produce something that my colleague, which is not here, Tim Henkes, did out of the HEP project, which already got mentioned sometimes right now. And this is one of the tape outs on a carrier board from HEP. And I just got the allowance to talk about it. It's made by open source tooling connected to the closed PDK of IHP 130. And another thing I was allowed just some minutes ago to talk about is the December tape out. The next iteration of this HEP project, RISC-V, shall be open source tools, open source PDK, and hopefully the SRAMs also in open source. Well, I think that is in the making. So, and this one already, open source tools, open lane, open road, connected to the closed PDK, does a compiled hello world. And I think it's capable of more, but what I got confirmed is it does a compiled hello world, which is very fine. Yeah, thank you. Back to our university, two things I want to mention is hackathons. Hackathons for sharing space on a multi-project wafer, like tiny tape out, and hackathons for producing standard cells in an open source manner. And I'm hopefully looking up for upcoming for teaching open source EDA in computer science together with Steffen in the next years. Sharing multi-project wafers is a way to get designs for a very cheap price and a very low entry barrier to the students. If you imagine sharing a multi-project wafer for 40 projects, and each of the 40 projects into maybe some 100 different designs, and you're sharing the costs for that, you're at the idea of tiny tape out. And luckily, it's not only available as a service from Matthew, tinytapeout.com, it's also the biggest parts of it. I mean, everything is open source and you can use it on your own. You can modify it, review, help and participate. That is the whole idea of open source. So what we're doing at our university with that is we have that low entry barrier for chip designs. We're doing one-day hackathons to bootstrap digital design with people who have never heard before of digital design. And we're doing that in the browser. There's a tool called Wokwi, where you can do digital designs in the browser that gives you Verilog, which directly went into a GitHub action and CI, and afterwards you're getting GDS ready for production. We were the first university to participate in that, and I think there's a lot more by the same time frame. It's fantastic. You should look into that. Next thing is, when you're open source, you can visualize stuff. So an open PDK with a layer documentation, the OpenGDS library, including some open source tools, equals to, you get printable STL files for your 3D printer. And my adaptation of a tool for the IHP 130 PDK is linked there, and you can create these STL layers in the picture on the right. And I participated in a hackathon at ETH Zurich and did my own cell for the IHP PDK, and I wanted to print that, but the time frame was too short and I didn't get it. So what I have is an IHP 130 inverter in pieces right now lying on my desk with some glue next to it. And this is the ready version in a scale 40,000 to 1, which means 1 micrometer is 4 centimeters. It's this one. I have even more of them comparing different PDKs, and I wrote a blog post about how to do that stuff. I have some of them with me, a few in my bags, and I would love to discuss with you people about these models, looking onto them and just having a discussion, what could be better in that models, what could be made better, and sharing. I don't want to take them home. So give a good reason for me to give you one and be the first one. Thank you, and Steffen, you might come up again for questions.